Well, hello everyone, and welcome back to Prep 34. So in this second tab, we have another two-sample z-test. It's going to be very similar to the tab we just did. A regional sales manager at a nationwide electronics retailer wants to determine if there's a difference in the average number of units sold per day between two divisions, the East and the West. To investigate this, she randomly selects sales data from her database. The sample data shows daily the units sold by sales associates from the East and West divisions. Assume the population standard deviation for East is 12 and the West is 15. That's what makes it a z-test, because we're given the standard deviations. At a significance level of 0.05, can the manager conclude that the mean number of units sold per day is higher for the West? Right, so we're, again, since it's higher means more, which means right. Distribution, we said, was z because we're given the population standard deviation. The null is that there's no difference, and the alternative is that West is higher than East. So x bar for the West is going to be that, and the standard deviation for the West was 15, given in the problem, and the number in the West is that. X bar for the East is there. Standard deviation was 12, and then the count for the East is that. All right, so we can see here there is a difference. Remember, these other smaller dots are, what it might have been, right? Where they might have been if this, if we'd have more variability. If we took samples again and again, they could come out anywhere. They could come out at any of these dots, or maybe even between the dots. We don't know. Okay, so the sampling distribution, but what we assume is if they really did come from the same population, then they should be spot on, right? Same sample mean. And if not, then the West would have come from a different population, so we would say there's a true difference. So we're going to assume a difference is 0, and then calculate the standard error. Remember, do this very precisely, or once you go down a rabbit hole of messing this up, you can be there for a while trying to figure out where the parentheses is. Okay. So our observed difference between the means is equal to that minus that, 2.75. So now you can actually look at these two numbers next to each other. So our observed difference was 2.75. Our expected difference, just by sample variability, would have been 2.85. So this is probably going to be a fail to reject, right? Because we're almost spot on, right? In fact, even a little less than what we expected. And you can see that right here, right? Because we're sort of in the tall part of the sampling distribution, right? We're not out here in the tail. Now, if the samples had been different, like if this, if the black dot, instead of being here, had been like over here, and the red dot had been, instead of being here, had been over here, well, that would have been a big difference. That probably would have been a reject. That would have been one of these gray dots way over here, but that's not what we found. So we're going to, in all likelihood, fail to reject. But let's keep going to make sure we do that systematically. But I just want you to know that you should start to develop a feel for the numbers, and so you should actually know at this point that this is not a reject, either from these two numbers or from this picture. So it's the observed difference divided by the standard error. And the probability of that is going to be norm.s.dist true. And remember, it's got to be the 1 minus, because the function looks to the left, but we're actually looking to the right. Okay, let's keep going. Alpha is 5% in all our problems, pretty much, unless we tell you that it's 1%. And norm.s.inverse to get what would be the z-score corresponding to each of these alphas. And then this one has to look the other way. And this is the one we'll actually use because we're one-tailed right in this problem. You can see it right here. There's the cutoff, 1.64, and we don't make it to that cutoff. We're not in the green area, so this is a fail to reject. But we'll go ahead and complete the confidence interval. So that was our observed difference, and then we take the observed minus the standard error times the number of standard errors you would expect in a two-tailed test, because confidence intervals are two-tailed, because it's our first purple band, which is the low end of the confidence interval, and then it's the same thing plus standard error times two-tailed right. So as you can see, our confidence interval squarely includes the hypothesized difference, which is 0, right, in a two-sample test. It's always going to be 0. We don't expect to see any difference. And since the hypothesized mean is right there, then this is a fail to reject. And so on this one, I'll let you, now that you know all that, I'll let you work with this answer block. And we'll see you in the next video.